Hey, this is Horner, and we're looking at Chapter 2 questions. These are concept questions. And the first one says there's a 15 Newton force and a 45 Newton force acting on an object in opposite directions. So we'll draw the first one, which goes over, and it's 45 Newtons. Then we have the second one that goes to the left, and it's only 15 Newtons. So the easiest thing to do here is just subtract two forces. We have one going to the right minus the one going to the left, and we end up with a 30 Newton force. So that would be your net force on the object. Question number 2 says, what's the maximum resultant possible when adding a 2 Newton force to an 8 Newton force? So if you remember, the very first thing we did was add these different forces. So let's say that this one's 8 Newtons. In order to get the maximum, I would not want to add it back the other way or add it up to the straight up and then have that line that we have here. Instead, we're just going to attach it right to the end of this one. So this would be 2 Newtons. So we're just going to take 8 plus 2, and we end up with a 10 Newton maximum resultant possible. For the next one, which is number 3, it says a 5 Newton force and a 30 Newton force act in the same direction on an object. What is the net force on the object? So let's just say that I've got a box and I have a 30 Newton force pulling the box. So maybe I have a something like, I don't know, have a gentleman over here. He's pulling, and then we have a young lady behind it, and she's pushing it, with a force of 5 newtons. So our answer for this one, obviously, is going to be 35 newtons, because all we did was we just take the 5, we add it to the 30, and we get 35, and it's because they're going in the same direction. So that one's pretty simple. For number 4, this one says, what is the minimum resultant possible when adding a 5 Newton force to an 8 Newton force? So if I have an 8 Newton force going in this direction, and I have a 5 Newton force going in this direction, the minimum resultant that I can get, so the smallest resultant I can get here, should be 3 newtons, because now I'm going to take 5 newtons away from 8 newtons, and that will give me that 3 Newton force, and that's the answer to number 4. For number 5, this one says equilibrium occurs. Well, there's a lot of different things we can think about equilibrium, but if we say that we have a box sitting on a table, okay, and that box is just sitting smack dab on this table, not moving, we can say that it is in equilibrium. Okay. You could also have a person just sitting on a swing. So here's a swing, then you've got a person just sitting on the swing, and they're not swinging back or forth, they're just sitting there. Equilibrium in all these cases, all the balance is on the box and all of the forces on the swing are balanced. So we know we have to have balanced forces for equilibrium to occur. All of the positive x need to equal all of the negative x forces, so that one's pretty easy. The sum of the forces, we've said this one before, should be equal to 0, and we also know that any force in the positive y should be equal to any force in the negative y direction. So those are the 4 things that you really need to know whenever you have a balanced force. For number 6, it says a girl whose weight is 500 newtons. So here's our girl, and her weight is mg, and so we know that she is 500 newtons. She hangs from the middle of a bar supported by 2 vertical strands of rope. So we've got a bar up above her, and then there's 2 strands of rope that come down and attach to her, and they are both vertical, so they are straight up and down. I know it doesn't look like it, but let's just pretend. So they're both up and down. They want to know what is the tension in each strand. So what we're going to do is we've got 2 forces of tension. I've got T and T. I know that was funny. And then we have coming down from the middle of the girl is mg. So let's do the sum of the forces for her in the y direction is equal to 0. I've got tension plus tension minus mg is equal to 0. So that means that 2 times tension minus mg is equal to 0. So 2 times the tension is equal to mass times gravity. We know her mass times gravity is 500 newtons, and we have 2t. Divide both sides by 2, and we see that the tension in each rope is 250 newtons, and that would be your answer. For number 7, that's the next question, it says the weight of a person can be represented by a vector, and this vector we know is always straight down. So I'm going to draw a person, and if I have that person, I know that that person's weight, if I go from their belly button down, is mg. If that person, let's say that they are standing on a hill, so here's a hill, and they are standing on the hill like this, we know their weight is still mg, and it is straight down. So remember, this is always, always, always straight down towards the center of the earth. For number 8, we have the question, what would be the safest way to put up a clothesline? And for this one, we actually want a little bit of slack in the middle. So you would want some slack in the middle. And it's because when you have slack in the middle, you can add clothes to it. So we're just going to put some things on it here. And then when it becomes taut or tight, there's not a tremendous amount of tension in it. If I already have a very tight line and I try to put clothes on it, that increases the tension by a lot. So if, let's say that each of these lines could hold 800 newtons, if it's really tight and it's supposed to hold 800 newtons, and I have several things and it just bends a little bit, we get a little bit of an angle, we'll end up snapping that. So you really just want slack in the middle, and that's really all you need to know about number 8. For number 9, we have a barge being pulled along a canal by 2 ropes that makes equal angles with the direction that the barge points. Assuming the 2 pulls on the barge are equal, what direction does the barge begin to move? So here's a barge, and let's actually make it brown here. So there's our barge. And we're looking on a top-down view, and there is water that the barge is in. So I'm going to draw my water that it's in, and it's being pulled by 2 ropes. So we're going to make these 2 ropes red, one going this way, one going this way, and they are equal and opposite. So if we think about our vectors, our components of our vectors, here's one, here is the other one. Notice they are both pointing straight down the water. Then remember, I have a vector going this way and a tension vector that is going in this direction. So we're going to call these two T horizontal. We're going to call these two T vertical. Notice that T horizontal 1 and T horizontal 2, so we'll call this 1 and 2, line 1 and 2. These two actually cross off. So if I did a sum of the forces in the x direction, that would be equal to 0. So T1 minus TH1 minus TH2 would be equal to 0. So they've got to be equal and opposite. So they actually cancel. For our TV1 and our TV2, those two, because they're going in the same direction, they actually add. So I would have TV1 plus TV2. And so because those add together, we know that it's got to move straight down the water in that direction. Next question is number 10. This one says a clothesline is stretched between 2 trees. So I've got a couple of trees here. So let's go ahead and draw our trees. Here's one tree. Here's the other tree. We'll put a little green on the trees here like that. And now what I'm going to do is put a line between them. So here I've got a lantern suspended by a pair of ropes with 120 degrees between them. So they're each 60 degrees from the vertical. So this would be 60 degrees, and then this side would be 60 degrees. The lantern itself hangs down like this. It is 100 newtons. And the thing that I want us to find is the tension in each rope. So they want us to find out what is the tension. Well, notice that this side of the triangle is opposite of our weight. Okay? And because it's opposite our weight, it could actually be the inside of that triangle here. So we've got a 90-degree angle here, 90-degree angle here. Here's our 60-degree angle. So we want to know what is this side. What is this side of the triangle? In order to find that side, what we're going to do is we're going to say that this is going to be 1/2 of mg. So remember, each side has got to hold up half. So I'm going to cross this off. I'm going to say this is really 50 newtons on this side and 50 newtons on this side for this triangle. So two triangles, we've broken it up. And let's go ahead and solve the rest of this one now. We have 50 is going straight down. So let's just draw one of the triangles here. So this side, 60 degrees, this side we know is 50. Okay, we want to know what is this side. So notice that this is the hypotenuse of our triangle, and this side is our adjacent side of the triangle. So we're going to say cosine of 60 degrees is equal to our adjacent, which is 50, over the hypotenuse. Now we're going to find the hypotenuse, and that's going to be equal to 50 all over the cosine, of 60 degrees. And so now if you use your calculator and you take 50 divided by the cosine of 60, what's funny is you do end up with 100 newtons in that rope. That's not a mistake. That's actually true. Doesn't hardly ever come out that way, that the weight and the tension in one side of the rope is the same, unless you have a 60-degree angle, and then at that point you truly do. So that's number 11. For number 12, you're helping your aunt move a piano on wheels from one room to the other. When you push the piano horizontally, it moves at constant speed. What can you say about that piano? So we've got our piano. Here, we're just going to make a really easy upright piano here. Kind of looks like this. It's on wheels, and we are moving it in this direction. Notice it's moving at a constant speed. When it moves at a constant speed, we know the sum of the forces is equal to 0. So we have balanced forces. When we have balanced forces, we can say that this thing is in dynamic, and that's because it's moving equilibrium. If the piano was still, okay, if it was still, so not moving, we would say it is in static equilibrium. So there's a difference between dynamic or moving equilibrium and static equilibrium. So if it's moving, it's got a speed and it's constant. It's got balanced forces, it's on dynamic equilibrium. If a piano was just sitting still, then it would be in static equilibrium. So that's the key, is dynamic equilibrium. For number 13, a scalar quantity has only one thing. And remember, that's only has magnitude. Okay, what's magnitude, you ask? It's a number. So it'd be like 5 newtons. You do have a unit, but there's no up, down, left, right, in or out. Okay, so if you said 5 newtons down, kind of like force due to gravity, you'd have to cross off the down. So the scalar would just be that 5 newtons. So it's just the number in the unit, or just the number if it doesn't have a unit. In order to find the components of a vector, we need to do several things. So let's say that I have a vector. If I want to find the components, I would have to first draw the vector. So I'm going to draw this guy with the correct magnitude and direction. So it wouldn't help me if I drew it upside down backwards. That would be bad. Next thing I need to do is I need to draw my triangle. Okay. Once I've done that, I've got to measure these sides some way. If I know the angle, okay, if I know the angle, that would be kind of easy to do. If not, I might be in a little bit of trouble. But if I know the angle, that helps me. But I'm actually just going to make a right triangle out of this, and then each one of these are going to be. This one is always, if you remember, it's the sine of the angle. So if we call this vector v, this one would be v sine of the angle, and this one would be v cosine of the angle. And that's really how you go through and find those different components. For the next question, for number 15, it says, what is needed to describe a vector quantity? So if you remember for this one, if I have a vector, I have to have magnitude. So that's like a number of some sort. So this is 5 newtons. And then I also need a direction. So the direction on this, let's just say it's 30 degrees. I also need a direction. And that could be an angle. That could be up, that could be down, that could be in, that could be out, it could be positive x. I think you get the gist here. It just needs to be able to tell both the magnitude, number 1, and the direction, number 2. And those are the conceptual questions for Chapter 2.